Hi everybody. I don't see that many people in the stream just yet, but we will get started here. Hopefully more people will show up shortly. What's on the agenda today? Oh look, it's more quantum mechanics, hooray. But there is a last call for lab worksheet number 3. I saw that there were some questions in the Discord. I'll try and get to those after class. I've been streaming all day, so I just haven't had time to do it. But that worksheet is due tonight. Make sure that you get that in before the midnight deadline. Let me click on this again real quick and see if this has changed at all. Not really. Okay. All right, so now what we're going to do is we're going to take everything that we learned yesterday. We're going to try and put it together into a diagram for electron configurations. And so what I'm going to do is I'm going to kind of go off script here for just a bit. We're going to review all of those quantum numbers that we did and show how to translate that into a picture. So we're going to go over here to start. And I'm going to make a diagram. And you're going to see this diagram like 60 million times in this class. So and I'm just making these longer to give me more space. All right. So we talked about 4 quantum numbers yesterday. We did N, L, M sub L, and then M sub S. I'll put N equals infinity up at the top here, just to have that handy. All right, what we're going to do is we're going to make an electron energy diagram. So the y-axis here, again, is potential energy. And there really isn't an x-axis to this. We're just going to arbitrarily place things on here in order of energy. So our ordering of energy is going to be based off of the principal quantum number n, and then we need to subdivide it for L, M sub L, and M sub S. So yesterday we said that for n equals 1, this will just be our workspace over here. L can only be 0. And if L is 0, then M sub L can only be 0 also. So what we're going to do is for each n, we're going to create bins that have our sublevels L in them. So I'm going to make a bin here, and this bin is going to be L equals 0. And for each bin, we're going to create our orbitals. And I'm going to create a number of orbitals equal to the number of possible values for M sub L. So I'm going to put a box here. That was a little too big. And there we go. And then, of course, we have M sub S. M sub S is always going to be equal to plus or minus 1/2. So when I do put electrons in here, I'm going to have the plus 1/2 and the minus 1/2. All right. Let's make the diagram for n equals 2. And so same thing for L equals 0. It's going to be M sub L is just 0. No problem there. So I'll make a bin that says L equals 0. And this will be M sub L equals 0. But over here, for L equals 1, M sub L can be -1, 0, or +1. So I'm going to make a bigger bin for L equals 1. And then M sub L equals -1, 0, and +1. Now, if you've done the reading and you've seen what these diagrams look like in the pictures, you can see that this is how we're constructing the diagram. This is why we care about all these silly quantum mechanics number rules, is so that we can construct this diagram, because this is how we represent electrons experimentally. This is like what we have observed them as far as their pattern is concerned. And then I can put my electrons in here like so on and so forth. So now if I wanted to identify an electron, so let's just say I'm going to pick this electron right here. I'll get a new color. I want this electron. This electron would have the quantum numbers n equals 2, L equals 1, oops, M sub L is -1, and then it's the positive 1/2 spin. So that would be that electron. The electron next to it would be the same thing with the opposite spin. So yesterday when we made all of those numbers, the first 3 numbers tell you what orbital you're looking at, which is this box right here. The last one tells you which electron. I'm getting pinged in the class Discord. Hold on. Oh, it's because people are doing the lab. That's why nobody's here. Okay. Yeah, if you want to watch the lecture later, that's totally fine. Oh, there's more people here now. Hooray, hello. All right. So, this is why we went to all this trouble to learn all these crazy numbers and what they represent. And then what we're going to do is, instead of referring to these as these numbers and with N and L like this, I'm going to instead start calling these by their N value and then the letter we assigned to them. So this is 1s. This is 2s. These are 2p. And so on and so forth. And so we can make the next layer n equals 3 in the same way. So let me clear this out of the way to give us some space for that. And we'll just erase this. So we'll do that. So for n equals 3, L can be 0, 1, or 2. For 0, the only possible value of m sub L is 0, like we covered before. For 1, it can be -1, 0, or +1. And then for 2, it can be any number between -2, not positive, and +2. Okay, let's draw our diagram. So here's the L equals 0. There's m sub L 0. Then we can do L equals 1. And then I'm going to need more space here. For L equals 2, m sub L, -2, -1, 0, 1, and 2. And this keeps going on and on and on and on and on infinitely. And if we were going to label these, this would be 3s, these would be 3p, and these would be 3d. So this is the general structure of what the diagram looks like. We're going to later change it very slightly. We're going to order the energy levels differently. But for a hydrogen atom with only one electron in it, this is what the diagram looks like. So let's put that note here. So H with one electron. Oh, I should probably say, so this diagram is for hydrogen with one electron. When there's only one electron present, and I realize I've drawn extra electrons in here for the example, but I would erase all of these and just have one electron in it. All these levels are going to be all the same for each n. Later on, that's going to change, and we'll talk about why. Okay, so that's where we're going with all of those quantum numbers that we just collected and then wrote out all the possibilities and all their addresses. This is the diagram that we're going to get to. At some point, you will get to the point where you just have the diagram memorized. You just spit out the diagram every time. And I'm going to show you a way to learn how to do that, to do it really quickly. And then, ironically, all of the headache that we spent on yesterday's lecture learning all these quantum numbers sort of fades away and we never use them again. Which is really frustrating because this is a very obtuse and esoteric sort of thing that we're doing. And we spent 2 hours on it and then you're never going to touch it again because it's all implied in the diagram. But sometimes that's just how science works out. All right, let's get started and let's talk about how we arrange electrons around an atom into this diagram. So the first thing we're going to do is we're going to write an electron configuration for any element in what is called the ground state. The ground state is the lowest possible energy state of our electrons. What that means is that since the energy is arranged on the or the y-axis going from lowest potential to highest potential, the highest potential being 0, where the electron is not attracted to the nucleus at all, it's too far away. We want our electrons to, in other words, be as close to the ground or the lowest possible space that they can go in on the diagram. So we can fill in the picture that we have here from bottom to top. start at n equals 1, fill in all the electrons you can. Start at go to n equals 2, fill in all the electrons you can. And then so on and so forth. We're going to start by writing those electron configurations out in a sentence, and then show that in the diagram. All right, so let's do an example with just hydrogen. Hydrogen has only one electron. What would its electron configuration be? Well, what is the lowest possible energy orbital in the diagram that we've got here? And so if I didn't have anything in here, I'm actually going to go back and erase all that while I'm talking here. If I didn't have anything in this diagram, anything being electrons, the lowest possible orbital available would be 1s. So if I put my electron in the 1s orbital, and in fact, what I'm going to do here, sorry, give me just a second here. So new layer, that didn't work. New layer, there we go. Now I can draw on that, and then I can just keep this forever. All right, so what is the electron configuration for hydrogen? Well, if there's only one electron, and it goes in the earliest orbital, the lowest orbital would be 1s. So what I would write is the following. So we put our element, we put it in square brackets, and then I write the orbital that the electron goes into, and then as a superscript, I write how many electrons I've put in that orbital. There's only one electron, so I just do that. So what do all of these terms mean? So the first number that we put here, this is just n. Actually, I should just hit the spacebar. The number that goes in the front is n. The character or letter that goes after that is the sublevel, but we use its letter code. And then the number that goes as a superscript is the number of electrons that are in that sublevel L. Now for an s orbital, there is only one orbital total, right? If I was looking at p orbitals, there would be 3 different p orbitals that I could put in there. So I could put more than one electron in p orbitals. In fact, I could put up to 6 because they pair. All right, let's do helium. What would I write for helium? Well, helium is 2 electrons. And I'm allowed to put 1 electron per orbital, or I can put a second electron in if their spins are opposite. So my electrons would go in the 1s orbital, and I would put both of them there. How about lithium? What would I do for lithium? Well, lithium has 3 electrons, so the first 2 would go in the lowest energy. But then I have to go to the next level. There's not enough space in the first orbital. All the orbitals are filled, so I go up to the next lowest energy. So that would be 2s, 1. And so we can start putting these things on our diagram, and then we'll put our electrons in there. So here they go. Here's our first electron, and here's our second electron. And of course, you got to make sure that you satisfy the Pauli exclusion principle. So we'll spin it around so that it can pair. So this would be what helium looks like. Now, if I have more electrons to put in more orbitals, I have to fill in more boxes. And so that's where our diagram will come in over here, which I'm actually going to have to adjust because we're going to have to change the energy levels of these. So I'll probably just redraw it real quick. That's okay. Now, I said before that when there is only 1 electron available, our diagram looks like this that I showed you before. But what happens when you start putting multiple electrons in there? For example, if I put a 3rd electron in for lithium, in my diagram here, I put it into S, but why couldn't I put it into P if they're all the same energy? Well, it turns out that when you have multiple electrons and multiple protons, they're not all the same energy. And the energy of the sublevels then comes into play, and they separate out a little bit. We're going to see that in just a little bit. In fact, we're going to see that right here. For a given energy level n, sublevels arrange in the following order. S is the lowest in energy, then P, then D, then F. What that means is that when I go back to my diagram, here's the diagram again, you're going to see it a lot. In fact, what I have to do is just sort of strong bed here. We're going to just select all and delete it. We're going to draw it again. We're going to draw it with the energy level splitting in mind. So here's my potential energy. Here's my nucleus. And I'm just going to skip over the bins and just draw the orbitals as they are. So we'll call this 1s. There's 2s. But we did just say that 2s is going to be lower in energy than 2p is. So I'm going to draw it a little bit higher up. And then we'll do the same thing for n equals 3. And there you go. Now, later on, we're going to run into an issue here because when I put n equals 4 in, you might think, oh, I should just put it up here, right? Well, it turns out n equals 4 is like right here. And you can see where the issue might be. These start to overlap with each other. So for now, this is going to be good enough, but we'll fix it later when the time comes. Why did I draw a dotted line through this? Who knows? That was silly of me. All right. So up to 3p, this will be correct. And that's what we're going to start with for now. All right. So I should have drawn that on that layer. So now I can do whatever the hell I want to. I should be able to just be like, ha ha ha, let's ruin my diagram. And then, oh, no, it's not ruined. Yep, there we go. Cool. All right, so now we have all of our orbitals filled in so that we can just drop electrons in for any species all the way up to 20 electrons, because that's going to go all the way up to 3p. Or actually, that's going to go up to 4s. So 18 electrons. We'll go up to argon here. So let's start doing some examples with n equals 2 electrons in here. So here's where our n equals 2 level is. We're going to put L equals 0. That's the s orbital, so 2s. And then for L equals 1, that would be the 2p orbitals. There you go. Just like we talked about at the start of the period. Now we know the order of the electrons, so if I give you an element that has this many electrons, we can fill them in the correct energy order. So let's do an example of that. Oh, we'll do that in a second here. Now, for 2p, all of these orbitals are at the same energy level. So all the m sub L values are equivalent. Sort of ran off the side there. That should say equivalent. There you go. And so what that means is that if you are putting in electrons in here, there will be some considerations that we'll note later. Any orbitals that are on the same position on the y-axis, we're going to give them a name. This is called degenerate. You know, what old boomers call millennials today, you degenerates, right? Something is degenerate when it has the same energy as other things. At least that's the term in math. In like society and culture, it means something very different. All right. Let's fill in our diagram for oxygen. Oxygen has 8 total electrons because it's element number 8. So we're going to fill them in one at a time, starting at the bottom. So here we go. 1, 2. We'll go to the next level. 3, 4. Then we'll go to the next level up here. 5. And then we have a choice here. Well, hold on. Should I do the 6th electron here? Or should I just put it in the next space over? And it turns out that this is the correct answer. Remember that with electrons, electrons repel. Electrons don't want to be paired with each other unless they have to, and if they have to, the opposite spin allows that to happen. Now, if I have 3 levels that are degenerate, putting in my electrons in the same energy, it doesn't matter where they would go, right? Because I'm putting them in the lowest energy space available every time. But pairing electrons causes repulsion, which means that to hold those electrons together, I would have to provide a little bit of energy, right? I would have to hold them in place, in other words. Or I would just have to disincentivize them from separating by having the energy levels be apart. For example, I would not do this with my 4th electron because there would be a large energy price to pay for that. Think of the diagram as like paying rent. You want to pay the lowest possible rent, right? So you go in the lowest possible orbital. Here, I could pay a lower rent and pair with something, or I could pay a higher rent and be alone. And since electrons only care about energy, they'll pair first before they go to the next level. But if everything is available in the same level, then they separate out, and they would feel like this. So how many electrons have we done so far? 1, 2, 3, 4, 5, 6. We have 2 more to do, so the 7th one would go here. And then the 8th one would pair, because it wouldn't go up here. That would be too high of an energy. It'll instead go right here. And I can pair any of these because they're all degenerate. It doesn't matter which one I pair. All right. So there's what it should look like. And now my slide is going to just put this in here. Doot, 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 doot. I don't know what Masubal means. I'm assuming that was a typo. But if you're getting towards electron pairs and non-bonding pairs and stuff like that, that's absolutely where this is coming from. So when you draw the Lewis structure of atoms and elements, you're going to see M sub L. Okay. Yeah, these M sub L arrangements are why electrons arrange as they do. And when we get to hybridization, which is going to change this diagram a little bit, in chapter 5, we're going to see, oh, this is why I draw some electrons as a lone pair and other electrons as individual electrons and use those for bonding. So this is where all of bonding comes from, is we make this diagram to show how the electrons exist in an individual atom, and then when we put them together, those orbitals will interact with each other and we get a result. Now, what did we do here? Here was the order that we filled in our electrons for this level. And the reason that we did this was because repulsion costs a little bit of energy. And so we would pair before we go up to the next level. But if everything is on the same level, we would just do them independently. And so this is called Hund's rule. Hund's rule says, put an electron in each orbital on that energy level before you pair it. So if you ever have degenerate orbitals, you're going to put 1 electron in each spot before you pair them. Now, for s orbitals, there are no degenerate orbitals, so you'll just put 1 in and then you'll pair it and you'll move on to the next floor. So when we go up here to 3s, which would be in this box, I would put in 2 and pair them both. But then when we got up to 3p, we would do 1, 1, 1 again. And then when we get to 3D, you would go 1, 1, 1, 1, 1 before you start pairing them, just like before. Now, if I wanted to write the electron configuration for this, let's just write down where we put the electrons in the diagram. So this is oxygen, and so this would be 1s2, because there's 2 electrons here, 2s2, 1, 2, 2p, 1, 2, 3, 4. And that would be the electron configuration for oxygen. All right, so now you can draw any diagram for any set of electrons and write the electron configuration by following this pattern all the way up to 18 is where we're going to stop for the first bit. So that's what I'm going to have you do. So sketch out a blank diagram of your own like this. And then what you're going to do is you're going to draw out the electron configuration diagram for each of these 3 atoms and also write the electron configuration sentence. Okay. Now you could do these in either order. Since you know the ordering of the energy levels, so you know it goes 1s, then 2s, then 2p, then 3s, and so on. You could either write the sentence first or write the diagram, fill in the electrons for how many electrons that there are, and then turn that into a sentence. Either way works. But what I want you to do is do both tasks for each of the 3 elements. Remember, you want total electrons. We have not gotten to valence electrons yet. So if you're thinking, oh, fluorine is 7 valence electrons, don't think of that. Just count the number of electrons by looking at the periodic table. If you don't have a periodic table handy, let me get the link for P table for you, which is right here. I've been playing a lot of Pathfinder Kingmaker, so I'm surprised that when I type the letter P, it doesn't say Pathfinder. I don't know why it says properties at the end, but that's okay. Anyway, there's an online periodic table. That's what I'm going to be using. And we'll go over the answers together in about 2 or 3 minutes. See you in a bit. Yeah, how many electrons does fluorine have? Be careful. Yeah, that is argon. That's correct. How do you know how many electrons an element has? Well, look at its atomic number. That's the number of protons it has, but these are all neutral atoms, right? So they'll have the same number of electrons too. All right, one more minute. We'll go over the answers. All right, so what I'm going to do is I'm going to write out the electron configurations on this page, and then we'll tab over to this thing over here, and I will fill them in. All right, so for fluorine has 9 electrons because it's element number 9. So we're going to write out the electron configuration in increasing energy until we get a total of 9 electrons. So 1s2, 2s2, 2p. I got 4 already, so that would mean I need 5 more. Remember that p orbitals hold up to 6, and then s orbitals hold up to 2. So 5, 7, 9, that should be good. Let's draw the diagram to show that that's the result that we get. All right, so over here, I got to make sure I'm drawing on the right layer, first of all, and I am. That's good. So for fluorine, I would go 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, which two you pair in this 2p orbital and which one's unpaired, totally arbitrary. You can have the single be wherever you want to, doesn't matter. The convention is that we work left to right. That's just what's done. So your fluorine diagram should look something like this, and that would be where your 1s2, 2s2, 2p5 comes from. So here's my 1s2, 2s2, 2p5. There you go. All right, let's go back to the lecture slide, and we'll do phosphorus. So phosphorus has 15 electrons, I believe. I gotta look, actually. Yeah, it's 15. And so that's going to be 1s2, 2s2, 2p, 6, 6, 8, 10. I need 5 more, so 3s2, 3p, 3. And all these numbers on the top should add up to your total. So I've got 2, 4, 6 is 10, 12, 15. Okay, so we'll go back over here, and I'm going to go like this and get rid of everything. And we'll start again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And so that should match up the sentence that we just wrote down. 2, 4, 10, 12, 15. There we go. I don't know why I'm not just looking at the diagram, but there you go. All right. Go back over here. Let's do argon. So argon has 18 electrons. So 1s2, 2s2, 2p, 6, 3s2, 3p, 2, 4, 10, 12, 6 would be 18. Perfect. There you go. And we'll go back over here. Delete it all. Start again. 1, 2, 3, 4, 5, 6, 7. Oh, hold on. Doing it wrong. 5, 6, 7, 8, 9, 10. I tend to do that when I don't care because I know I'm going to the next level, but I should really be filling these in correctly. 15, 16, 17, 18. And so let's write out our configuration again, just so it's on the screen for you to see. In case you pause the video and look here. There you go. So that'd be argon. Now, earlier we said, we were talking about line spectra, and how electrons that travel up and down between these emit various colors, and the color depended on where you started and where you fell to. We said that as you add protons to the nucleus, these all fall down, and that's true. So the diagram that I am showing is not going to be the same energy. For example, if I had fluorine versus argon, the energy of fluorine would be much, much less negative than argon, because argon has way more protons, so it would pull this energy down much farther. So the number would be a much larger negative number for argon. And then the n equals infinity would still be 0 up here. However, we're not really going to concern ourselves with the energy levels too much just yet. We'll deal with that conceptually later on. But for our purposes, the diagram will always have the same appearance. So the orbitals will still be ordered in this manner. 1s, 2s, then 2p, then 3s, then 3p, and so on and so forth. You're going to explore this in more detail in the next lab that you're going to do next week, which is photo emission spectroscopy, which is basically I put the sample into a detector, and I shoot X-rays at it that cause its electrons to go, ah, and they all escape. And the detector detects how much energy it took to make those electrons escape. And it says, oh, okay, well, if I put in this much energy to get my electron to escape, so like I put in this much energy, here's my electron now, it has escaped. That must mean that the electron had that potential energy. And so you can plot that. So that's where that's going to occur on next week's lab. We'll talk about that later. Now, the next order of business that we're going to have to deal with here is what do we do after elements on 18? Ah! Hold on. I hit the wrong button. Are you sure you wish to remove this? No. Never remove. I almost deleted the entire... What am I doing? What? Select all, delete. I was trying to delete the writing on the diagram. I almost deleted lecture preview from my slide. That would have been bad. That would have just meant that everything just went and disappeared because I hit a button. Okay. What do we do for elements past 18? And the answer is, well, the ordering of energy becomes irregular. And the reason for that is because if I go back to this diagram over here, when I get to n equals 4 actually appears right in here. And so when I put 4s down, it's actually lower in energy than 3D. And then I put 4p down, and it's higher in energy than 3D. But you can see that when I get to 5s, I'm going to put like 5s in here or something. And it's going to mix all in here, and it's going to become really obnoxious to deal with, right? Because as these energy levels get closer and closer and closer and closer together, the spreading that occurs between the sp and d orbitals causes them to fall into other orbitals below them. And so we have to deal with that. How do we deal with that? Well, we use this diagram over here. So first I'm going to show you this diagram. And this is going to look really obnoxious. Like, how the hell are you supposed to memorize this diagram? It's actually super easy to draw. So here's what we're going to do. We're going to make this diagram. First, I'm going to hide this layer. Boop. Now I can draw all over it, and you just can't see it. I can just turn it on later. Boop, boop. So let's make that diagram first. We're going to list all the s orbitals. So 1s, 2s, 3s, 4s. And I'm just going to stop at 8, even though 8 is a little too far, but that's fine. Then I'm going to list all the p orbitals. Well, p starts at 2. And then I'm going to list all the d orbitals. D starts at 3. This is surprisingly difficult, and I don't know why. And then I'm going to list all the f orbitals, and f starts at 4. And then what we do is we start at the top, and we're going to work in this direction. And we're just going to draw lines through all the orbitals, just one at a time. Whoop, whoop, whoop. Notice how this slash got 2 of them. Whoop, there's 2 more. There's 3 more. And you just keep doing this over and over and over and over. And the order in which you've crossed them out is the order of the orbitals in terms of their energy. So I started here. And I just went do. So I would go 1s, that's the first one. Then 2s. Then 2p, then 3s. Then 3p, then 4s. Then 3d, 4p, 5s. Oops, sorry. Wrote the wrong letter. And then 4d, 5p, 6s. And then 4f, 5d, 6p, 7s. And then keep going as far as you need to go until you get all of the electrons that you need. So now you can draw an electron configuration for literally any element on the periodic table. So that's what we're going to do. We're going to start drawing electron configurations for really big and obnoxious elements. Now, this diagram that we have here, this is called the Aufbau Principle. You fill in your orbitals from the lowest energy to the top. Aufbau means filling from bottom to top, or filling up, or something like that. It's German. I don't know. I don't speak German. So this weird diagram tells us the correct ordering of energy for all of the orbitals that we will ever encounter. So one of the things that my students would do, the very first thing when they got the quantum mechanics exam in class, is they would draw this picture. And I'd say, when you get your exam, flip it over and just do a data dump. Write down anything that you want to. And everybody would draw this picture. And it's totally valid. So my recommendation to you is either to learn how to do the picture so you can just sketch it on a piece of paper, or have this slide handy and just refer to it. Whatever works. It's an online class, right? Do whatever you need to. But do know that this is the order of how you fill our electrons. Now, why does this happen? There's a bunch of text on this screen. And there's a phenomenon called electron penetration. The old textbook that I had went into this for a lot of discussion, and we're going to touch on it a little bit later when we talk about Z effective. But suffice it to say that when you have electrons in orbitals like the s orbital, they tend to be lower in energy by a significant amount compared to, say, p or d or whatever. And so s orbitals drop so far that they start to fall in before corresponding higher or lower energy level d and f orbitals. And the reason for this is due to electron probability. What's the probability of finding an electron near the nucleus? Well, for s orbitals, it's really high. So, since being closer to the nucleus corresponds to being lower in energy, s orbitals are lower in energy than other orbitals. For p orbitals, it's not as high, and for d orbitals, it's even lower still. That's the short version of electron penetration. Your textbook says it in a sentence. Don't worry about it. I'm not going to test you on electron penetration, so nobody cares. I mean, I care because it's cool, but your textbook doesn't care, so I'm just going to skip over it. Fill in your electrons in this order is the takeaway here. Here's another diagram of what your energy diagram will look like due to this. For our purposes, we're going to just take our energy diagram and just slide in the orbitals wherever we need to so that they're in the correct order. In fact, what you can do is you could just write them from top to bottom, or I'm sorry, bottom to top here. And you don't even have to use an x-axis. You could just put the 2p orbital, put it right here, and put the 3p orbital right here, and then put the 3d orbital in next. And that's fine. Okay, let's fill in some electron configurations for bigger elements. So what I want you to try and do before we do this example together is I want you to write out the electron configuration for zinc. Don't draw the picture unless you have a lot of paper handy. Okay, so write out the entire electron configuration for zinc. Zinc, for reference, is element number 30. So you should have 30 total electrons when you're done. We'll go over the answer in about a minute. Now, typing this out into the chat is probably going to be super obnoxious. So what I'm going to do is I'm going to just write it out. And the answer is going to appear right in front of me, so I might as well just go down here. So there's 30 electrons, and we're going to fill them in the order of the Aufbau principle. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. How many more do I need? 2, 4, 10, 12, 18, 20. There you go. Perfect. 30. So that should be the electron configuration that you get there. All right. Now the next one I'm going to give you is just rude. Here's uranium. Uranium has 92 electrons. Write the electron configuration for uranium. Because I hate fun. Go ahead and do it. I'll give you a whole minute and a half to do it while I go fetch p table, because I need to crop it for the next bit that we're going to do. Don't mind me, I'm just cropping this table real quick. I can't actually see it unless you can see it too. So we'll use that in just a second. All right, how far did you get? Now, a strategy that you can employ for these larger electron configurations is you could just write out the Aufbau principle first and leave a little space between each one. Oops, I already messed up. And then what will come after 5s? So that would be 4d. I'm trying to do this from memory. I always just draw out the diagram myself too, so. Where is my diagram? Oh, I can just look at the thing here. Hold on. 1, 2, 3, 4, 5. Where am I? 1, 2, 3, 4, 5. So yeah, 4d. 5p. 6s. 4f. 3, 4, 5d. 6p. 7s. 5f. And I don't actually need to go further than that. And now you just add in all the electrons. So 1s holds 2, 2, 6, 2, 6, 2, 10, 6, 2, 10, 6, 2, 14, 10, 6, 2, and then however many more I need after that, because I know it ends in the 5f block. So 2, 4, 10, 12, 18, 20, 36, 38, 48, 54, 56, 70, 86, 88. I need 4 more, so there you go. So if it works for you to go stepwise, that's totally fine too. But that should be the answer. And so when I hit the spacebar, I should end on 5F4, and it totally did. Like, what the hell? Why is my answer so long? And unfortunately, that's just the answer, right? Now, that's frustrating to work with, but there is something that you can do to help you. And that is that we're going to use the periodic table. So let me turn on this. I'm going to make this as big as I can without covering up the answer. All right, so if you've noticed that looking at the periodic table seems to be split into these weird shapes, right? Like there's a big gap here or whatever. And what the periodic table corresponds to is these electron configurations. So here's 1s2, it's this first row. Then we have 2s2, and then 2p6, 1, 2, 3, 4, 5, 6. Notice there's 6 in this row right here. Then 3s2, 3p6, 4s2, 3d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at that. 4p6, 5s2, 4d10, 5p6, 6s2, and then we go down here, and this is F. These are 4f14. This would be 5d10. Now, notice that there's 15 or so. There's probably 15 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so... Wait, hold on. Did I miscount? 5, 6, 7, 8, 9, 10. I did miscount. Okay. So here's 14. This last one is actually... One of those is the D that should go in this spot here, where we put the shortcut. So then 1, 2, 3, 4, 5, 6, 7, 8, 10. So that would be 5d10. 6p6. Here's 7s2. And then 5f, 1, 2, 3, 4. So that's how we get to it. So you can use the periodic table to sort of see where these blocks are. So everything over here is S. This is the S block on the left. Everything on the right here is the P block. This is all P in here. Excuse me. Transition metals are D. And then the intertransition metals down here are F. I unfortunately can't write on this screen because it's a web page. But for the period number will correspond to S and P. For D, you're going to have one lower than the period number. So this would be 3D, 4D, 5D, etc. And then for F, it's 2 lower. So instead of 6, it'd be 4. And then instead of 7, it'd be 5. Now, why didn't I just show you that at the start? Because it's really cool once you've done all the legwork, and now you can just copy it off the periodic table all the time, right? So that's exactly what I want you to do. Don't try and do this by hand or memory or whatever on the next slide when we do these, but we're going to take a break first. So you could try these over the break if you want, but I've given you these ginormous elements. In fact, one of them is like a radioactive one, dubnium or whatever. Yeah, 105. Write the electron configuration for all of these things using the periodic table. You just do it really quickly. But you're going to do that when you get back. So we'll take our break now. Is my timer up? Yeah, it is. Okay. So let's go get more Donkey Kong Country 2 music. We're getting to the part of the soundtrack that's probably the best. And of the best songs, there's one in particular that everybody loves. And it's this one. Enjoy. Oh, that's the second time I've gotten exactly 10 minutes today. I think that deserves a celebration. Where are we? There we go. That's what we want, right here. Yay. There was extra stuff on that video that I found very quickly. That's okay. Okay, so we'll go back here. And what I'm going to do, and you're going to see why I'm going to do this in a second. I'm going to do the first one of these for you. And so I'm going to use the periodic table that I have in front of me to do this problem. You're not going to actually do them unless you've already done them. That's fine. So I'm going to pick mercury just because it's somewhere in the middle there. And so mercury would be, so let's go through the periodic table. So 1s2. You can do this along with me if you'd like. 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Why did that happen? 10, 4p6, 5s2, 4d. How many? 10. 5p6, 2, 3, 4, 5, yeah. 6s2, 4f14. I keep holding the cursor down too long and what I'm writing disappears. 5d10. There we go. There's the answer for that one. Oh, it's so much work. Isn't there a better way? Do I have to draw these out every single time? No. Let's cheat. So, how do we cheat? And the way that we cheat is, well, if I write down the electron configuration for an element, so here's barium. Barium is just before mercury. And here's its electron configuration, which is really, really long and tedious, and sure, I trust that you can do this by now. But what if I looked at a reference point for each of my elements? And the reference point we're going to select is a noble gas. So I'm going to look at the noble gas that comes before barium. And the noble gas that comes before barium is xenon. Now, if I write out its electron configuration right here, I can take all of this that I have right here and just substitute that back in right here. Because here's that same thing, right? Here's xenon. This is xenon. So why do more work? I'll just find xenon, and we'll just start from there, right? Here's my xenon. We're going to substitute it out. There you go. Isn't that so much nicer? Why didn't we start with that? Because you have to learn the hard way before you can do it the easy way. That's just how science works, I guess. I don't know. So now, instead of drawing, here's the same elements. Minus xenon. I took xenon out of there. Here's the same elements that I had on the previous exercise. What I want you to do is write out the electron configuration, but use the shortcut. Use the shortcut method by referencing the noble gas that comes before it. So for germanium, you go backwards to argon, and you'd start by writing this. And then you just keep going. So after argon would be 4s2, 3d10, 4p, however many I need, 2. There you go. Easy. Way less time, right? Do that for mercury and dubnium and cesium. Okay? I'll check on you in about 3 or 4 minutes. All right, should be good to go in 1 more minute or so. So, if you get something, try and type the short version of your answer into the chat if you can. I realize that that's kind of still tedious, but like cesium, you could definitely do. All right, let's go over the answers. So we'll get mercury out here. I just drew that ridiculously long electron configuration for mercury. We're going to shorten it down here by starting at xenon, which is the noble gas right before mercury, although it's quite a ways before. And then we'll go to the next row, which is 1, 2, 3, 4, 5, 6 S2, 4 F14, 5D10. And there you go. That's all you have to write. Remember how I was like writing all the way down to the next line? Yeah, you don't have to do that anymore. All right. Whatever the hell this is, it's radioactive. I don't even know who this is named after, but all these radioactive elements are named after people who contributed to chemistry or physics in significant ways. So this would be radon, is the previous noble gas. And then the next row would be 7s2, 5f14, 6d, 1... Oh, I gotta count this right. 1, 2, 3, it looks like. I gotta make sure there's 14 on the bottom row. 7, 8, 9, 10. Yeah, mine has 14 on my table. I have a different table printed out than P table. And then cesium. Oops, I didn't mean to mark there. Cesium's super easy, so we'll go to xenon, and then we'll just do the next one. Boop, there you go. All right. Hopefully we are able to write all this out. All right, that's electron configuration. So we have taken all of the information from quantum mechanics and distilled it down into this sentence. And we could put these in a diagram if we wanted to. Like, you could draw an electron diagram for mercury. It would just be really, 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 really tall, because you'd have to go all the way up to 5d10, which is very far down the Aufbau chart. All right, so let's talk a little bit more about what we've done. We have written out all of the electrons in their configuration for a given atom. Let's be a little more specific, because that specificity is going to be relevant to us in Chapter 4 when we start talking about bonding. So the first thing we want to talk about are what are called valence electrons. If you've taken Chem 140, you already know what valence electrons are. Valence electrons are the electrons on the outside of the atom. These are the outermost electrons that another atom would bump into and participate in bonding. Now, for all the elements that you worked with in Chem 140, which was just all the elements in the groups 1 through 8A, you just counted all the electrons that were in the highest level N, and that's still true. But what about transition metals? Do transition metals have valence electrons? In Chem 140, we just said, we're not going to talk about it. But now we are going to talk about it. And what I'm going to tell you is special. So this is just a little sort of inside information. At Everett Community College, there are only 2 inorganic chemists. One of them is Anne, and she doesn't teach 161 anymore. She just teaches 121. The other one is me. And so I studied this extensively. And so I can tell you that what's on the slide is technically right, But it uses something very advanced. It's called Slater's rules, and we're going to talk about this a little bit more when we get to Z effective, probably on Tuesday next week. But counting valence electrons in transition metals and lanthanides and actinides is kind of silly and dumb. And so what I'm going to do is I'm going to highlight this in red and just ignore it. Just ignore these rules right here. For our purposes at this level, we don't care about D and F electrons being valence electrons. And what we're going to just say is that the valence electrons for any element are just these. The electrons in the highest energy level N. This is what you care about. So when you look at an electron configuration, you're going to look for the highest N. And those electrons are the valence electrons, and then you'll count them. So let's do an example here. So if I write out the electron configuration for, say, chlorine, I'm just picking an element at random here. I would write neon, 3s2, 3p, 5. What are the electrons in the highest N? Well, the highest N is 3. So I would want all the electrons in N equals 3, and so there are 7 of them. So chlorine has 7 valence electrons. That matches up with what you learned in 140, right? It's in group 7. It has 7 valence electrons. Let's do tellurium, which is deeper down in the periodic table. We can apply the same thing. So we'll take its noble gas configuration, which is krypton. We'll go to the next row. So that's 5s2. Where am I going here? There we go. 4d10. 5p. It's tellurium. It should be 4, right? Yeah, there we go. All right. What's the highest N? The highest N is N equals 5. So I only want these valence electrons. So that would give me 6 valence electrons. Now I ran out of space, so I'm going to have to hit clear on here real quick. So we'll give you a second. You can pause the video if you need to. Boop. And then I'm gonna underline this again because this is still true. Now we're going to pick a transition metal. And so your text is actually going to differ from this because your text was not written by an inorganic chemist. It was probably written by a general chemist or an analytical chemist. And so for my class, the way I teach this, if I pick a transition metal, such as like, say, cobalt. So we'll write its electron configuration. Argon, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. What are the valence electrons? Your textbook's just going to say all of these. But I'm going to say just those. And I'm going to put under here, for our purposes. And this will save us a lot of headache later on. Okay? So just remember, the highest energy level N, for our purposes, is going to be the valence electrons. Because later on, we start ionizing stuff and changing the number of electrons in our configurations. If we don't make this assumption now, we're going to have to remember a bunch of exceptions. And it's going to be super frustrating. Okay? So again, just ignore your textbook when it says this part. It is technically true, but we're not going to deal with Slater's rules in this class. It's too complicated. So here are some more examples that we can do for valence electrons. So we already did fluorine. Any electron that's not a valence electron is called a core electron. So core electrons are just buried under the valence electrons. So there are only 2 classifications of electrons. You're either a valence electron, which means you're on the outside and you participate in bonding, or you're a core electron and you don't. Now, again, that's not the entire story. Later on, when you get to 300 level chemistry, d electrons actually do really interesting stuff in terms of bonding. But for our purposes, they're not going to. We're not going to care about d electrons ever in this class. When you get to 300 level chemistry, you can learn it then. When we talk about inorganic chemistry and pi back bonding and Jahn-Teller distortion and all these words that Steve remembers from his inorganic, but he's not an inorganic chemist, so that's all he knows. All right. So what I want you to do is, for each of these elements that I've written down here, I want you to write out the electron configuration. It says write out the complete. You don't have to do that. So just, you could do the shortcut if you'd like. And then what I want you to do is I want you to circle the valence electrons. And I want you to underline the core electrons, okay? Use my definition. So all your transition metals, you're going to find out, oh, they all have 2 valence electrons. Yeah, that's sort of the gimmick of transition metals, is they have 2 valence electrons, which will be interesting later on. Okay, so write out these electron configurations and do these tasks. Circle the valence electrons, underline the core electrons. And we'll get back to you in just a bit. All right, 1 more minute and we'll go over the answers. All right, here we go. So let's write out the electron configuration for each of these. I have the highlighter selected. I need the pen here. So silicon would be, we're going to write down neon. And then the next row would be 3s2, 3p2. So we're going to circle the valence electrons. So the highest n will be our valence electrons. So these all are in the highest n. And then we'll underline the core electrons. That's just everything else. Easy as that. For nickel, we've got argon, 4s2, 3d, and I want to say 8, right? Yeah, 8. All right. What's the highest n? N equals 4. So these will be my valence electrons, and these will be my core electrons. Now, your textbook will count those d electrons as valence electrons, but for our purposes, don't worry about it. Just circle the highest n. Bromine will be argon, 4s2, 3d10, 4p5. What's the highest n? N equals 4. We'll circle that one, and we'll circle this one. We'll underline everything else. Everything else is a core electron. And then finally, argon. Guess what? You can't just do this. That doesn't tell you anything, right? So we have to go to the previous noble gas, which is neon. 3s2, 3p6. Highest n is 3. My core electrons are everything else. Notice how I underlined the noble gas configuration every single time? That's because those are always just going to be core electrons. They will never have the highest n if we're using the electron configuration shortcut by doing this. All right. Now that you are experts at writing out electron configurations and drawing them in a picture, let's talk about the weird random exceptions that exist. Okay. Not all elements fill exactly following these rules. There's a slight deviation for some of them. And here's what we observe. These exceptions occur with transition metals, and these are the ones that we're going to care about. Okay, so if I asked you to write the electron configuration for chromium, you would probably write this down. You'd say, okay, I'm going to go grab the noble gas before it. That's argon. And I think this should be 4, yeah. And you'd write this for chromium. And I wouldn't criticize you for that because that's the correct answer following the rules that we've done. But it turns out that when we experimentally observe chromium, we get this as the result. Notice what the difference is here. Instead of having a 2 and a 4, we get a 1 and a 5. Why the heck would chromium do that? It turns out that if we look at another element, we also observe this. So for copper, if I write its electron configuration out, we get argon, 4s2, 3d, 9. But what we actually observe is this. Why does that happen? And specifically, this only happens if I can end on a 10 or a 5 by moving 1 electron from S to D. So why does this happen? And the answer is that if we go back to our diagram that I haven't shown you for a while, and I go boop, boop. Now our diagram didn't have 4s in here. Oops, why can't I draw on this layer? Oh, because I don't have it selected, that's why. Oh, I don't want to draw on this layer. Hold on, let's just get rid of all this then. Okay. If I add in my 4s energy level, it would go right around here, right? So here's where 4s would go. Now, there is not much difference in energy between 4s and 3d. So when I'm filling my electrons, I would still do this before I start filling these guys. But because there isn't that much energy difference, when I get to a full configuration, remember how I said that as you add electrons, these shuffle about? These start to get closer and closer and closer, and this energy distance disappears. And so 1 electron will hop over to fill in the last space if I can land on D5 or D10. So we are only going to move 1 electron from S to D if we get D5 or D10 as a result. So this is just a weird experimental observation that we notice, is that everything in the chromium group, so that is group, what group is that on my periodic table? 6? Yeah. Everything in group 6, and also 11, these elements take 1 electron from the s orbital that's next to the d orbital, and they shuffle it over the d orbital to get d5 or d10. This is just what we observe, and the reason for this is because the s and the d are so close in energy that they do this, but only when they get extremely close. And that is because these energy levels are slowly decreasing as we put electrons in them. That's to do with penetration and stuff like that, which we unfortunately have skipped over due to this textbook. So the rule for this is called the half full or completely full rule, but it only works for transition metals. So if you can get half full or completely full by moving only 1 electron, and that's an important caveat, so we'll write that in here too. By moving 1 s electron. Then the result is what we'd expect. It'd be more stable. And again, this only applies to transition metals because the d orbitals and the s orbitals just happen to be close in energy every time. This will not happen for elements in the P block. So this will not happen for carbon, for example, or oxygen, or nitrogen, or whatever. So that won't happen. Only transition metals. Now, there are exceptions to these exceptions, and we're going to ignore them. Like, ruthenium is weird. As you cram all the energy levels together, the electrons just start to dance, and they just fill in sort of randomly. For the most part, they follow all the rules that we set out so far, and all the elements in the columns we just mentioned, so that would be the chromium group and then the copper group, will follow this half-full or completely full rule. We steal 1 electron at most. Those are the exceptions that I want you to know. So on the exam, if I ask you, what is the electron configuration for chromium, I want you to write this out. Okay? Don't go looking it up on p-table for the exception. So like if you wrote out ruthenium and you just copied off p-table, Canvas would mark it wrong, because we're just going to treat it as use the pattern we've established so far, except for these half-full and completely full exceptions. All right, so make a note of that, because you are going to see these exceptions pop up. Now, you can do these electron configurations on your own. So molybdenum falls in the chromium group, so it will have the exception. Silver also. Cadmium, however, doesn't. It already is D10. You don't need to move any electrons. So I'm going to leave these as exercises for you to do, but they should all end on D5s or D10s just as reference, because we're out of time for today. When we come back next week, we're going to talk about how to do electron configurations for ions, which is basically just saying, oh, okay, what do I do if I do this? What's its electron configuration? Or if I do this instead, what's its electron configuration? For anions, it's as simple as you think. You just stack more electrons. But for cations, it's a little bit more complex. We'll discuss why that is when we get there. Other than that, that's all I got. So tonight you do have a lab that is due. Make sure you get that in. I see that people are in the Discord discussing it right now, so I'm going to go and try and answer questions for them. But otherwise, have a wonderful rest of your evening. Turn in the lab to Canvas for the deadline, and we'll see you next week. Have a good one.